Okay, can you all see my screen? I guess not. Hold on, let me.
I can see your screen.
Oh, you can? Okay, good. All right, so let me come back to the PowerPoint here. Okay, so the last thing we discussed was using the ideal gas equation to get another equation for calculating the molar mass of a gas. And this is the formula that we derive. The molar mass, which is represented by uppercase M, is equal to the mass in grams times R, which is the molar gas constant, times the T, temperature in Kelvin, divided by the pressure times the volume, right? And I remember doing this example here where we simply apply the equation, right? To find the molar mass, which is numerically the same as the molecular mass, right? And if I recall, I told you guys to look at this question where you're to calculate the molar mass or the molecular mass of a liquid that when vaporized at 100 degrees Celsius and 755 torr yields 185 mils of a vapor that has a mass of 0.523 grams, all right? Whoops, sorry about that. So that's the example we're gonna start off with right now. So let me open up my little writing pad right here. Get rid of all of that. Now, hold on 1 minute. Let me just do something quickly here. Okay, so the equation we're going to use again is uppercase M is equal to lowercase m times RT over PV, all right? So the question now becomes, what do we put into these terms right here? So the first thing I see here is that the mass is 0.523 grams. So this is going to be equal to 0.523 grams multiplied by R, which is 0.0821 liters atmospheres over mole Kelvin times the temperature, which is 100 degrees Celsius, which you have to convert to Kelvin, which becomes 373 Kelvin. All of that divided by the pressure. Now, what's the pressure? So let me go back to the question. The question says that the pressure is 755 torr. So that means that we have to convert 755 torr, down here. Okay, why is it not writing? 755 torr. We have to convert that to atmospheres. So to convert it, we're gonna have 1 atmosphere above and 760 torr below, all right? And then we have to multiply that by the volume. And if I remember correctly, the volume is 185 mils, which we have to convert to liters. So I'm going to do that here. 185 milliliter. And we convert to liters by multiplying by 1,000. I'm sorry, 1 liter over 1,000 milliliters. All right. So you're going to see some units canceling out. For example, the torrs will cancel out here and here. The milliliters will cancel out here and here. The atmospheres will cancel out here and here. The kelvins will cancel out here and here. And the liters will cancel out here and here. So the only units remaining would be grams over moles, which would be the unit of molar mass. So where's my calculator? So we have to do some number crunching here. 0.523 times 0.0821 times 373 divided by 755 times 760 divided by 0.185. Okay, so, oh shoot, I accidentally cleared it. Let me do it again. 0.523 times 0.0821 times 373 equals that, divided by 755, divided by 760, and then divided by 0.185. Okay, so according to my calculations, this works out, how many sig figs? Let me see here. Okay, so I have to round off to 3 sig figs. So according to my calculations, this works out to be equal to 87.1 grams per mole. All right, so that's basically how that is done. Any questions about this example? Any questions? Any questions?
I don't think so. No.
Okay, well, let's move along to discuss another equation. Let me scroll down here. That you can determine, this time determining the density of a gas. So we're starting from this equation right here. Let me go to full screen mode. We're starting with this equation here that we just used, right? This is the equation that we use to calculate the molar mass of a gas. Now we can rearrange this equation to get m over v on one side, and that will be equal to uppercase M times P divided by RT. And as we all know, m over v is mass over volume, which is the density. So therefore, the density of a gas can be calculated by using this equation right here. The density is equal to the molar mass of the gas times the pressure divided by R times T, all right? So we can use this equation to solve problems. But before we get to that, I just want to point out a couple of features of this equation right here. If you look at this equation carefully, you'll see that the density here is dependent on several factors, right? So for one, everything else being the same, the greater the molar mass of a gas, the greater would be its density, right? Same thing is true for the pressure. There's a direct relationship between the pressure and the density of a gas. And then down here, you'll notice that there's an inverse direct relationship between the density and the temperature. In other words, the higher the temperature, the smaller or lower would be the density, right? So those are just some interesting relationships between the density and some other variables, all right? Okay, so with that out of the way, let's look at an example right here. So in this case here, they gave you the formula for methane gas, they gave you the temperature, and they gave you the atmospheric pressure. So let me go to my writing pad here again. Okay, so the equation we're using is the density of a gas is equal to MP over RT, all right? So the gas is methane, CH4. So we have to find the molar mass of methane. So again, being the lazy person I am, I'm going to go to my trusty molar mass calculator. And I'm going to put in the formula for methane. I know it's 16 point something. I just don't remember exactly what, CH4. Okay, and then let it calculate. And according to this, it's 16.04. All right, so I'm going to put here 16.04 grams per mole. And we're going to multiply by the pressure. So according to the question, the pressure is 0.978 atmospheres. So we're going to put 0.978 atmospheres, all divided by R, which is 0.0821 liters atmospheres over mole Kelvin. And then we get to the temperature. Now, what did the question say about temperature? The question said that the temperature is 25 degrees. Okay, so that means we have to convert that to Kelvin. When you convert that to Kelvin, you're gonna get 298 Kelvin. All right. Okay, and then of course we do our unit cancellations. You're gonna have moles here canceling out. We're gonna have atmospheres canceling out here and here. And the Kelvin will cancel out here and here. So you'll be left with grams per liter as your unit of density. And then I'm going to multiply 16.04 by 0.978 divided by 0.0821 divided by 298. So the answer I got, how many sig figs? Okay, 3 sig figs. So the answer I got is 0.641 grams per liter. So that's how you do that. And let me just say that usually, and I think I made this point before, but it doesn't hurt for me to say it again. Usually, the density of gases are expressed in grams per liter. That's the most convenient units for the expression of density. For solids and liquids, we typically express densities in grams per mil or grams per cm cube, all right? Okay, any questions about this particular example? Any questions?
I'm good.
Okay, so moving along. Okay, so that's that. Okay, so here's another example. Under what pressure must O2 be maintained at 25 degrees Celsius to have a density of 1.50 grams per liter? So in this particular case, you're using the same equation. Let me go back to, all right, let me just clear everything up. Yeah. Okay, so the same equation is being used, which is, as I said before, D is equal to MP divided by RT, all right? Now, in this particular case, the question is asking for the pressure, right? So what we have to do is rearrange this equation here to get P on one side. And when you do that, you're going to end up with P is equal to D times RT over M. So all we have to do now is put the numbers in. So according to the question, D is equal to the density, which is 1.50 grams per liter. So we're going to put 1.50 grams per liter times R. What is R? Same thing, 0.0821 liters atmospheres over mole Kelvin. Times the temperature. What's the temperature? Well, let's see what the question says. The temperature is 25 degrees Celsius. So again, we have to convert to Kelvin, which would be equal to 298 Kelvin. Whoops. 298 Kelvin. And then we have to determine the molar mass. And that's easy because the gas is oxygen. So all you have to do is multiply 16.00 by 2. So that gives you 32.00 grams per mole. And again, we do our unit cancellation. The grams cancels here and here. The moles go as well. The Kelvin cancels out here and here. The liters will cancel out here and here. So your final answer will be expressed in atmospheres. So do our calculation here, 1.50 times 0.0821 times 298 equal divided by 32.00. And we have to round off to 3 sig figs. So therefore the answer becomes 1.15, write it here, 1.15 atmospheres. And that would be the pressure of the oxygen, all right? So, you know, these are just different examples, you know, basically using the same equations, but of course you have to know how to manipulate the equation, algebraically rearrange the equation to get what the question is asking for, and then you plug the numbers in. And let me just say, if I have not said this before, I'm a stickler for units and sig figs. So when you're doing these types of calculations, make sure that you show the work, make sure that you show the units, and make sure that you round off your answer to the correct number of significant figures, all right? Okay, any questions about this example? Any questions? Any questions?
I think we're good.
Okay, so far so good. All right. So now we're going to talk about reaction stoichiometry, gaseous reaction stoichiometry. So in this section of this chapter, we'll be combining what we learned earlier with respect to stoichiometry with what we just learned about gases, right? So if you remember, stoichiometry is that area in chemistry which deals with the quantitative relationships between different substances involved in a reaction. So we're just basically applying those same principles that we learned then to gaseous reactions or reactions involving gases, right? Now, the first thing I'm going to talk about here is what is known as the law of combining volumes. And this is the law basically stated in words. It says, when gases measured at the same temperature and pressure are allowed to react, the volumes of gaseous reactants and products are in small whole number ratios, all right? So that is the law of combining volume. So what this is saying is that if you have a reaction taking place between gases to produce gases, and all the gases are at the same temperature and pressure, then what you'll find is that the ratio of the gases involved as reactants and products will exist as small whole numbers, and in fact will parallel the small whole numbers which would represent their coefficients in the balanced equation. So for example, if you have the reaction between hydrogen and oxygen, right, from water, right? Let me remind you of the equation for this reaction. Let me do this here. So it is H2 gas plus O2 gas to give H2O gas, right? Now, of course, by now we all know that to balance this equation, you're going to need a 2 here and a 2 here, right? And what you're going to find is that these numbers here, the 2, the 1 here for the oxygen and the 2 here, represents not only the mole-to-mole relationships between the different substances, but they also represent the volume relationships between these substances. In other words, 2 volume units of hydrogen will react with 1 volume unit of oxygen to form 2 volume units of water vapor, right? And it doesn't matter what the volume units are. They could be, you know, milliliters, gallons, centimeters cubed, liters, whatever, right? So this is basically what the law of combining volume is saying. It's saying that the volume ratios here will basically parallel the mole ratios for reactions where gases are involved, all right? Now, please note that there's one constraint on this law, and that is that the temperature and the pressure must be constant for each of these gases. So the temperature and pressure must be the same in order for this law to hold true, all right? Another example, let me go back to the PowerPoint here. Okay, why is this? Okay, another example. So we just dealt with the example of hydrogen and oxygen, right? And explained the 2-to-1 ratio in terms of the volume. Another example is the reaction between nitrogen and hydrogen to form ammonia. So let me do that equation right here. So it is nitrogen plus hydrogen to give you ammonia. And again, we have to balance this equation. So to balance this, we're going to need a 2 here, and we're going to need a 3 here, right? And again, the mole ratios would be the same as the volume ratios, provided that the temperature and pressure are the same for all gases involved. So in this case, it would be 1 volume unit reacting with 3 volume units of hydrogen to form 2 volume units of ammonia. So that's basically how this law works. Okay, and based on this law, you can do some examples. But before we, hold on, let me go to this here. But before I make that point, or before I go on to those examples, I want to reemphasize the point I made earlier, right? The temperature and pressure must be constant. We don't even need to know what the temperature and pressures are, as long as the conditions are the same for all the gases. As long as the conditions are the same for all the gases, then this law will hold true, all right? Okay, so here is another pictorial example of the reaction between hydrogen and oxygen to form water. It's a 2-to-1-to-2 ratio, not only in terms of moles, but also in terms of volume, where the temperature and pressure are fixed, all right? So the ratio of the volume, the ratio of the volumes is the same as the mole ratio, which is the point I made earlier. All right, okay, so based on this law, you should be able to do problems such as this problem right here, right? Now, this question says that you have a compound known as pentane, which is a liquid, and it is burnt in air to form carbon dioxide and water. So the question is asking for the volume of oxygen that is needed when it burns the pentane for every 10 liters of carbon dioxide. So my question to you is, what would be the very first step you would take in order to solve this problem?
Probably you would balance the equation.
Right, you need to obtain a balanced equation. So that means you need to identify what the reactants are and what the products are, right? So,
Oh, is this one of
let's-
those deceptively difficult problems?
well, not really. It's just that you need to know, well, it's just that you need to know basically, you know, what to start off with. So
Mhm.
let me clear this up. Okay, so what are the reactants? One of them would be pentane, which is C5H12, which is a liquid, plus oxygen, which is a gas. And the products will be what?
Carbon dioxide
Mhm.
and water.
So CO2, gas, and H2O, which I think is a gas in this case, because let me go back to the question and see how it's worded. Oh, it doesn't say. So it could be a gas, it could be a liquid. Not important in this case anyway. And then what's the next step? After you have the unbalanced equation, what do you need to do?
Well, then you would need to balance it. So
And how would you go about doing that?
Let me think here. It looks kind of complicated. You would need, let's see, however many pentane molecules.
Well, you have to look at the number of atoms. Remember, when you're balancing, you're basically making sure that the number of atoms of each element are the same on both sides.
So let's see here. We're probably going to need more than one. Let me think. 2, 10, 5, 24. Let me write it out real quick.
Yeah, that's what you need.
So I
Yeah,
don't
you
get
need to put pen
confused.
to paper. You need to put pen to paper in order to do problems like this.
So say for each, 12 over here, 12. All right. So we've got 10C, 24H, 32O. Here, 10C, 20 plus 12.
Oh, come on, folks. It shouldn't be that difficult.
Yeah, I'm getting to it. Yep, I've got it all figured out now.
Okay,
So you would need 2 pentane molecules to 16 oxygen molecules, which would yield
16 Uh-huh.
Which would yield 10 carbon dioxide molecules and 12 H2O water molecules.
Okay, let me see your.
And I believe.
Yep, that looks right. Okay, so far so good. So the next step is basically given 10.0 liters of carbon dioxide, how many liters of oxygen do you expect to get? So we start off with the 10.0 liters of CO2, and then we multiply by a volume ratio, which represents the relationship between O2 and CO2, and that's 10 to 16. So we're going to put 10 liters of CO2 down here, and 16, hold on, is that correct? Okay, 16 liters of CO2 of O2. I don't know why I'm blanking on this. Okay, so basically the answer would be 16 liters of O2. And I just realized something. You could have actually divided all these numbers here by 2 to get simpler coefficients, right?
Oh,
So
probably.
So this is
I was
1, this is 8, this is 5, and this is 6. It doesn't change the answer though. The answer will still be the same, but I'm just saying for future reference, you want to get the lowest possible integers for the coefficient of the different substances involved in the reaction. All right. What's that? Oh, another mistake I just made. This should be
I was
16.0. Hold on. This should be 16.0 liters because this is 3 sig figs. All right. So this would be 3 sig figs as well. Okay. You were saying?
Oh yeah, I was just confused on the CO2. I was just a little bit confused on that, and I forgot to correct it.
Yeah, sometimes that happens. All right. So if there are no questions on this, let me go back to the PowerPoint here, and let's talk about now other situations of gas stoichiometry. Now, all the examples that we have looked at before in terms of gas stoichiometry, we were assuming that the temperature and pressure for all the gases are the same. As you can imagine, that may not be the same. That may not be so in our cases. So we have to know how to deal with that. So as stated here, we only use the law of combining volumes if and only if the temperature and pressure of the gases are the same. Otherwise, we have to go back to what we learned earlier when it comes to stoichiometry to deal with other situations where the temperature and pressure are not the same. And we have to combine what we learned with the ideal gas equation. So basically, we can summarize most, or I would say, in fact, all stoichiometry problem by this approach here. We start with moles of substance A. We use the mole ratio based on the balance equation. And then we multiply moles of substance A by the appropriate mole ratio to get the moles of substance B. That is basically what stoichiometry comes down to. I mean, there are other situations where you need to calculate the moles of substance A, or you need to calculate from moles of substance B other things. But basically it comes down to this, which underscores the importance of having a balanced equation to begin with, because the balanced equation gives us the mole ratio, which is correct. Now, as far as gases are concerned, we have to use the ideal gas equation. So the ideal gas equation is PV is equal to nRT, right? So basically, if we're given a problem where we're given PV and T, and of course you know what R is, then you'd have to use the ideal gas to find the moles, and then you do the mole fraction calculation, and then, you know, whatever the question is asking for, you go ahead and try to solve the problem that way, right? If gas B, if B is a gas, we can solve for the moles of B, again, using the ideal gas equation, all right? Or if you get the moles of B more correctly, then you can find PV or T using the ideal gas equation. And we're going to see an example of this right now. So here we have a question. It says, it's talking about the chemical reaction that is used in automotive airbag safety systems. Now, to be honest, I don't think they use this anymore. I think they use something else. But back in the day, they use sodium azide. Sodium azide, when you subject it to a sudden impact, or if you drop it, you know, let's say you have some in a bottle and you drop it, it produces a gas, right? So the gas is what fills out the airbag and protects the driver and the passenger from head injuries and so on, all right? So they gave you the reaction for the formation of the nitrogen from sodium azide. And the question is asking, what volume of nitrogen measured at 25 degrees and 0.980 atmospheres is produced by the decomposition of 62.5 grams of sodium azide? Okay, so let me do this here. So basically the question comes down to this: 62.5 grams of NaN3, and the question is asking the volume in liters of nitrogen produced, all right? So the first thing I would do is start off with the 62.5 grams of sodium azide, and I would convert it to moles. So 1 mole of NaN3 divided by the molar mass. So again, I am going to go to my trusty molar mass calculator. No, that's not it. This is it. So here it's going to be NaN3. I'm going to calculate. And according to this is 65.01. So I'm going to go back to here and okay. I hate these hiccups. Now, why is it not giving me the pen function? Okay.
You could try pointer options.
Where is that? Oh, let me see. Where is it? Oh, pointer option.
Right
Okay,
there.
thank you. Okay, now I forget what I what was the molar mass I got? 65.01. Okay.
65. Yep.
Yeah, 65.01. So I'm going to put 65.01 grams of sodium azide down here. Okay, so the next step would be the mole ratio between the sodium azide and the hydrogen, I'm sorry, the nitrogen. And you see here, there's a 2 here and a 3 here. So I'm going to put 3 moles of nitrogen above 2 moles of sodium azide. 2 moles of NaN3. Okay, so need to work that out. 62.5 divided by 65.01 times 3 divided by 2. Okay, so the answer I got after rounding off to 3 sig figs is 1.44 moles of nitrogen. And this would be the N that would be in the ideal gas equation. Now remember, the ideal gas equation is PV is equal to nRT, right? What the question is asking for is V. So V would be equal to nRT over P. So all we have to do is put the numbers in. So we calculated N, which is 1.44 moles, times R, which is 0.0821 liters atmospheres over mole Kelvin, times T. What is T? 25 degrees Celsius, which is 298 Kelvin, all divided by P, which according to the question is 0.980 atmospheres. And that's basically what we need to do. So let me do the calculation here. 1.44 times 0.0821 times 298 divided by 0.980. And the answer I got is 35.9 see it here, 35.9 liters. And that's basically the final answer. All right. Any questions about this example?
Well, not really, but that's quite a lot of gas from 62 grams.
And that's how it works. That's why they used it in the airbags, right? You just need a small amount, relatively speaking. Well, 65.5 is kind of large, but I mean, in terms of size, you know, you just need that amount to produce that much in terms of volume of gas. I think that I need to look this up because I think they use something else. I'm going to look it up and find out exactly what they use nowadays. Okay. Okay, so next topic, Dalton's law of partial pressures. Now, all along, so far, we have been dealing with just situations where we're assuming we're working with one gas, right? What Dalton's law is talking about is the pressure of a mixture of gases. And basically, Dalton's law states that the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures exerted by the separate gases. All right, so basically what this law is implying is that each gas acts independently when exerting pressure, even if they're in a mixture. So mathematically speaking, we can write the law like this. P total is equal to P1 plus P2 plus P3 plus whatever number of gases that you have present, all right? Now, each gas acts independently, right? And therefore, each gas, you can write an equation for its pressure, right? So for gas 1, the pressure will be P1 is equal to N1 RT over V. For gas 2, the pressure will be P2 is equal to N2 RT over V, and so on and so forth. Now, let's see what would be the consequence of this here. Go back to my writing pad here. Okay, so as I said before, for gas 1, P1 would be equal to N1 RT over V. For gas 2, P2 would be equal to N2 RT over V. For gas 3, P3 would be equal to N3 RT over V. So you'll notice in each case, the T and the V would be the same because they're in the same container. If they're in the same container, the temperature would be the same and the volume would be the same. So the only thing that would be different between the gases would be the number of moles, and therefore the pressure would be different as a result of that. So, as we said before, according to Dalton's law of partial pressure, PT would be equal to P1 plus P2 plus P3 all the way to Pn, right? So what I'm going to do is plug in each of these terms into their respective positions in that equation. So for P1, that would be equal to N1 RT over V. For P2, that would be N2 RT over V. For P3, that would be N3 RT over V, plus all the way to Pn, which would be Nn RT over V, right? And then what we can do is factor out RT over V, and we're going to end up with N1 plus N2 plus N3 plus all the way to Nn times RT over V. And we can replace all of this here with simply NT. NT is the total sum of the moles of all the gases in the mixture. So therefore, this simplifies to this equation. The total pressure would be equal to the total moles. Shucks, I keep doing this crap. Sorry about that, folks. Right, so the total pressure is equal to the total moles times R times T divided by the V, all right? So that's how you can calculate the total pressure of a gas based on the ideal gas equation. Of course, you'd have to know what the number of moles of each gas is so that you can add them together to get NT and then plug it into the equation to get P total. Okay. Any questions about what I just discussed here? Any questions? Any questions?
No, makes sense to me.
Okay, so let's look at a pictorial representation here of Dalton's law demonstrated here. So here we have two gases. We have hydrogen, 0.6 moles, and the pressure is 2.9 atmospheres, and the volume and temperature is given here, right? Here we have helium, same volume and temperature, but the pressure is 7.2 and the number of moles is 1.5 for helium. So if you were to add these two together with the same volume and temperature, you're going to end up with this situation. And you'll notice here that the total pressure here is the sum of the 7.2 and the 2.9. And of course, the total moles here would be the sum of the 0.6 and the 0.5 moles, right? So that's basically what Dalton's law is saying, all right? Now, here's a question here. I want you to think about it and tell me how you'd go about solving this problem. The question here is, what would be the total pressure if 0.90 moles of nitrogen were added to the mixture in C? So we're talking about this one right here, right? So how would you solve this problem?
Well, first I would go and add the molar mass of the nitrogen to it, which would be 3.
Add the moles.
3.0 moles altogether. Let me plug that into the equation. 3.0 times 0.0821 times, what is the temperature? 273 plus 20 is 293, all divided by the volume, which is 5.0 liters. And give me a second and I'll work that out. 3.0 times 293. And that's gonna look like 14 liters.
Okay.
Rounded to 2 sig figs.
Well, I don't know what method you use, but
Oh,
does if you use a more
that's not it.
complicated. Well, I'm not saying it's not right. It seems as if you use a more complicated method. What I would do is I would basically recognize the fact that the total moles is proportional to the total pressure, right? So you correctly calculated that the total moles, well, let's put it this way. The initial moles is, the initial total moles is 2.10 moles, right? And then when you add the nitrogen, it increases to 3.00 moles, right? So
yeah,
the total pressure initially was 10.01, right? So to find a new pressure, you do a proportional relationship, right? So basically the new pressure, we put PT, would be equal to 10.1 atmospheres times 3.00 moles, 0 moles, divided by 2.10 moles.
Oh.
And if I plug this, 10.1 times 3 equals divided by 2.1. You got 14, right?
Yep.
Yeah, so 14 is the answer. So your answer is correct.
Well, that's...
I mean, the way you did it is not incorrect, just longer than the way I would have done it. So this would equal to, in fact, if you round off, you need to round off to 3 sig figs, so it should be 14.4 atmospheres.
Oh, but I went and I calculated it with the molar mass of nitrogen in my equation.
Right.
Okay.
Yeah, so yeah, this is a shorter way of solving the problem. All right. Okay, moving along. So let's look at this example right here. It says a 1 liter sample of dry air at 25 degrees contains 0.0319 moles of nitrogen, 0.00856 moles of O2, 0.000381 moles of argon, and 0.00002 moles of carbon dioxide. Calculate the partial pressure of all the gases in the mixture and the total pressure of the gaseous mixture. All right. Okay, so let's see here. They gave you the volume, they gave you the temperature, and they gave you the moles of each gas. And they're asking, oh, okay, so they're asking you to calculate the partial pressure. So this is kind of, what's the word I'm looking for? This is kind of long-winded, well, not really long-winded, but kind of repetitive because you have to calculate the pressure of each gas. It's the same process. You're gonna use the ideal gas equation, P is equal to nRT over V, right? So let's start off for nitrogen. For nitrogen, Pn2 would be equal to the moles, which is 0.0319 moles times R, which is, of course, always the same. Times the temperature, which is 298 Kelvin. All divided by the volume, which is 1.00 liters. All right. So you have to work that out. 0.0319 times 0.0821 times 298 divided by 1. Okay, so according to my calculations, this works out to be equal to 0.736, so 0.780 atmospheres. All right. And basically, you're going to do the same calculation for the other gases. I hope I have enough space here. The pressure of oxygen would be equal to the moles, which is 0.00856 moles times 0.0821 liters atmospheres over mole Kelvin times the temperature, which is 298 Kelvin, all divided by 1.00 liters. And let's see what that gives. So that would be 0.00856 times 0.0821 times 298 divided by 1. So in the case of oxygen, rounded off to 3 sig figs, that would be 0.209. Scratch this out. 0.209 atmospheres. And then we do the same thing for the third gas, which is argon. So the pressure of argon would be equal to the moles, which is 0.000381 moles times 0.0821 liters atmospheres over mole Kelvin times the temperature, which is 298 Kelvin, all divided by 1.00 liters. And let me do that calculation here, 0.000381 times 0.0821 times 298 divided by 1. Okay, so the answer I got here is 9.32, 9.3, oh, wait a minute. Oh, 9.32 times 10 to the minus 3 atmospheres. All right. Okay, I'm running out of space here. So where shall I squeeze? Let me try to squeeze that here. For carbon dioxide, PCO2, That would be equal to 0.00002 moles times R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 298 Kelvin, all divided by 1.00 liters. Okay, so let me work that out. 0.00002 times 0.0821 times 298 divided by 1. So the answer I got here is 1.6 so this should be 5 times 10 to the minus 4. So this is going to be 5 times 10 to the minus 4 atmospheres. Okay, so that's basically how we calculate the partial pressure of each gas. And then to answer this part, to get the total pressure, all we have to do is add these values together. All right, so let me do that. So
Oh, you don't have to. I already did that. The total pressure, it ends up being, with the correct sig figs, 1 atmosphere.
1 atmosphere, yeah, I kind of figured so. Yeah, when you add them up, you're going to get 1 atmosphere, exactly. So that's basically how that is done. Okay, any questions about that? Any questions about this example?
No, not really.
All right, moving along. Okay, I want to introduce to you something which I doubt you have met before. The concept of mole fraction. The mole fraction is basically a way of expressing concentration. And it can apply to any type of mixture, but for our purposes now, we're going to apply it to gases. So what you see on the screen here is the definition of mole fraction. The mole fraction by definition is the number of moles. Well, and let me just say this, the mole fraction is specific to one component in a mixture of different components, all right? So by definition, the mole fraction of a component in a mixture is equal to the number of moles of that component divided by the total moles of the mixture, all right? So that's the definition of mole fraction. And based on that definition, assuming that the volume and temperature of the gases are the same, we can use pressures to express the mole fraction. So as you can see down here, the mole fraction of a gas, 1, is equal to the pressure exerted by that gas divided by the total pressure of the gaseous mixture, right? So those are just 2 different ways of expressing the mole fraction. Even though the first one is a definition, the second one is useful when it comes to doing certain calculations. All right, so based on what we have just learned, we could do this example right here. It gives you the percentage of the different components in a gaseous mixture. And the question is asking what is the partial pressure of each gas in a sample of air 1.00 atmosphere. And this is, again, kind of repetitive, but it's very easy actually. Let me go to my pointer function here. Okay, so basically, I'm just going to do the first one and you should be able to figure out the others. The partial pressure of nitrogen will be equal to the percentage, which can be expressed as a mole fraction, which is 0.7808, times the total pressure, which is 1.000 atmospheres. And that's it. The answer in this case would be 0.7808 atmospheres. And basically, you're going to do the same calculation for oxygen, for argon, and for carbon dioxide, right? It's the same idea. You just simply multiply the mole fraction by the total pressure, and you're going to get your individual pressures, all right? So I'm going to leave you to try that on your own. If you have any problems, just let me know. But it should be relatively easy for you to solve this problem.
So this kind of question is pretty easy when it's like, it has 1 atmosphere.
Right, exactly. Because that's the total pressure of the gaseous mixture, yeah. Okay, now let's talk about this sort of situation where we collect a gas over water. There's certain gases that you can basically trap above water in the lab, right? So if you prepare these gases in the lab, then this would be an ideal setup for such gases. Now, this only works for certain gases, right? It works for gases that will not dissolve in water, all right? So we're talking about gases like oxygen, which does dissolve in water, but not by much, right? Nitrogen, hydrocarbon gases, and so on. This would not work for gases like hydrogen chloride or ammonia or any such gas, right? So what you're seeing on the screen here is basically the setup for such a collection. You have your jar, right? And initially it would be full when you invert it into the water. So you have your trough with the water right here. And then you have your hose leading from wherever the gas is being generated, leading into the jar. And as you can see here, as the gas is escaping from the hose right here, it collects above the water surface right here and basically forces the water level down, all right? Now, important fact here you need to note here is that the gas that is collected here will not be the pure gas. It will be saturated with water vapor. So you're gonna have the gas here and the water vapor. So that's what the question is asking here. What two gases are present here? If oxygen is a gas generated, then the two gases that would be here would be oxygen and water, right? Water vapor. So typically when this experiment is done, we collect the gas until the water level here inside the jar is at the same level as the water level outside the jar in the trough, right? And we do that because we want to make sure that the vapor pressure, or I should say the atmospheric pressure or barometric pressure that acts on the surface of the water here outside would be equal to the pressure of the gaseous mixture that is inside, right? So therefore, we can say that let me just write it right here. P bar will be equal to the water vapor pressure plus the vapor pressure of the gas, which in this case is oxygen, right? So therefore, or let me just put gas here, or G for gas, right? So therefore, if this is true, then down here, this is true, right? The pressure of the gas will be equal to the barometric pressure minus the vapor pressure of water, all right? Now, the barometric pressure, of course, you can measure using the barometer, and the vapor pressure of water, you can actually get from tables that provide that data. They will give you the data of the vapor pressure for, every temperature, like for every degree, starting from, I think, 0 degrees, all right? So, well, not 0 degrees, actually, from, well, maybe from 0 degrees, who knows? But anyway, you can get those values, and then based on those values, you can determine what the pressure of the gas collected in this setup is, all right? And I think the next slide is an example of a question where that is being looked at, right? So what this question is describing is what we just discussed, right? Hydrogen is produced based on this reaction that is given, right? And the question is asking what volume of the wet gas will be collected in the reaction if 1.50 grams of aluminum reacts with excess hydrochloric acid, all right? They gave us some other additional information. They gave you the vapor pressure of the, let me see here. They gave you the vapor pressure of water, and they gave you the barometric pressure, all right? So you're gonna need that information as well. So how do we calculate this? All right, so let me get out of this here and go to my writing pad. Okay, so the first thing I'm gonna do is start off with the 1.50 grams of the aluminum, and then I'm going to convert that to moles. So you're going to have 1 mole of aluminum here, and the molar mass of aluminum, which I think is 27. Where's my table? Oh, you know what? I'm going to cheat again. So I'm just going to put AL. and see what it says. I think it's 26.9 something. Yeah, 26.98. So going back to this, no, going back to this, I'm going to put 26.98 grams of aluminum, all right? And then the next step would be the mole ratio between the aluminum and the hydrochloric acid, or I should say between the aluminum and the hydrogen. And if you look at the equation that is given in the question, you're going to see that for every 3 moles of hydrogen, there are 2 moles of aluminum, all right? So this would give you the number of moles of hydrogen. So 1.5 divided by 26.98 times 3 divided by 2. Okay, so according to my calculations, this works out to be equal to 0.0834. Is that right? Let me do this again. 1.5 divided by 26. Oh, wait a minute. I think I know what I did wrong. 1.5 divided by 26.98 times 3 divided by 2. Oh, that's right. Okay, so 0.834 moles of H2. And this is going to be the N in the ideal gas equation. Now, the question is asking for the volume. So basically, this is the equation we're going to use. V is equal to nRT over P. Now, we know what the N is because we just calculated it here. We know what R is. R is always going to be the constant. And T, we know what the temperature is because that is given in the question. T is 22 degrees Celsius, which we have to add 273 to get 295 Kelvin, all right? Now the question now becomes, what is P? P would have to be the pressure of hydrogen. And the pressure of hydrogen in this case would be equal to the barometric pressure minus the total pressure. Or I should say the vapor pressure of water, which is pH2O. So if I do that calculation over here, I'm gonna have 742 torr minus 19.8 torr. So 742 minus 19.8. So the answer I got is 722.2, which you have to round off to 722. So I'm going to put 722 as the answer for this part right here. Okay, so we have everything we need to solve for V. So I'm going to plug in the 0.0834 moles times 0.0821 liters, atmospheres over mole Kelvin, times the temperature, which is, as I said before, 295 Kelvin, all divided by P, which we just calculated to be 722 torr, but we have to convert that to atmospheres. 1 atmosphere over 760 torr. Okay, so let me do my calculation here, 0.0834. 0.0834 times 0.0821 times 295 divided by 722 divided by 760. So according to my calculations, this works out to be equal to 2.13. 2.13. And in terms of units, it's going to Okay, any questions about this example? Any questions? Any questions? Okay, well, moving along. Let me see what's next. Okay, I think this will be the last topic for today. So let me just go through it quickly. All right, so the kinetic molecular theory, as we said before, is the model that is used to explain the behavior of gases, right? So these are the principal assumptions of the theory. A gas is made up of molecules that are always moving around in high speeds and in straight line motion. On average, the gas is mostly empty space because on average, the molecules are far apart from each other. Very important, the next one, the next assumption, there are no intermolecular forces between the molecules, right? Except when they collide with each other. And then the last one in this list here is saying that the individual molecules may contain or may gain or lose energy as a result of collisions. However, the total energy remains constant, right? And I think in physics, the term for that is that the collisions are elastic. So basically what they're saying is that when the particles collide with each other, there's basically transfer of energy from one to the other, but the overall situation is that there's no total loss of energy, all right? And based on what we just talked about, one can derive this equation. Now this equation, don't worry about it. You don't need to know about it. I'm just showing you this simply because I have to, because it's an equation that is basically derived from the kinetic molecular theory. So basically what this equation is saying is that the pressure is equal to 1/3 times the number of molecules divided by the volume times the mass of the molecule times this term, which is the average of the squares of the speeds of the molecule. And this shows you the relationship between the pressure of a gas and some different terms. So for example, the greater the number of molecules, the greater would be the pressure, right? The lower the volume, the greater would be the pressure, which of course comes from, which relates directly to Boyle's law, the inverse relationship between pressure and volume. The greater the mass, everything being the same, the greater would be the pressure. And of course, the greater the speeds of the molecules, the greater would be the pressure exerted by the gas. So that's basically one equation that comes directly from the kinetic molecular theory. And then there's another equation which relates the energy of the particles or the energy of the gas to the temperature. Again, you don't need to know this equation right here, but the important point I want to show you is that there is a direct linear relationship between the average kinetic energy of the molecules and the temperature expressed in Kelvin. As the temperature increases, the kinetic energy of the particles increase as well, which of course we all know it makes sense. You increase the temperature, you're imparting energy to the particles and they will move faster, all right? Okay, I'm gonna stop here for today. But before I finish, let me just say that, or remind you that I've posted the test number 1, and that is due on the 18th, all right, which is Friday, all right? So make sure you download it, complete it, and scan it and upload it. Please remember, upload it as a PDF document, and make sure that you write your name on each page, all right? Very important. Make sure you write your name on each page so that just in case there's some mix up when I'm printing it, I can basically put your individual tests together, all right? Okay, finally, let me take roll quickly and then that's pretty much it. Let me go to, where is that page? Okay, and today is the 15th. Okay, Rios. Okay, not here. Barber is here. Cannon, not here. Chang, not here. Chavis, Clark. Is Clark here? Oh yes, Clark is here. DeGraff, Franklin, Han, Panic, Aaron is here. Holland is here.
Here.
Jurgensen is here.
Here.
Rees, not here. Rose, not here. Ronalds is here. Santiago is here. And Smith is here. Okay, very good. All right. Are there any questions, any issues, any problems?
I had a question about the test real quick.
Yes, ma'am.
So on question 1, it's asking us to perform the mathematical operations and then result
hold on.
in the, oh, sorry.
Let me bring it up.
Okay.
I never expected a question on the test, so let me go here. No, please note, I cannot give you any direct answers to the test. So
Okay.
if I'm a bit cryptic, please forgive me. I can only try to guide you. Okay, what question is it?
I was just wondering, so like the first 2 parts, you want us to convert into like the same unit of measurement, or is it just about the sig figs?
It's about the sig figs, but also you have to include the correct units in your final answer.
Okay.
All right, so both things I'm looking at, sig figs and your units.
All right.
Mhm.
Thank you.
All right.
Mhm.
Any other questions?
I had a question.
Yes, ma'am.
I was wondering if you could re-upload the quiz answers because the file wouldn't work.
I'm sorry?
I was wondering if you could re-upload the quiz answers for quizzes 1 through 4 because the file wouldn't work.
Oh, really?
Yeah.
Ooh, okay, let me check out something here. I did not know that. So the quizzes, the quiz answers, okay. Okay, yeah, there's a problem. I don't know. Okay, I'll have to see if I can figure that out. I'll try to get that done. Well, I won't. I'm going to go on campus. Okay, I'll go on campus tomorrow and try to get. I can't promise I'll get it done today, but I plan to go on campus tomorrow, so I'll see if I can take care of that. All right.
Okay, thank you.
All right. Okay, any other questions? Okay, so if there are no other questions, that's pretty much it for today. So I'll see you guys on Thursday. All right?
All right. See you
All right.
Thursday.
All right, take care.
Take care.